Okay, good afternoon, welcome back. This is lecture 24, and as always I will begin with a quick recap of what we were discussing last time. So, in the last lecture we were looking at other examples of the MPF problem, and the examples that we were looking at related to the decoding of codes, and our first example had to do with the maximum likelihood decoding of a block code. So, you can see that here that we showed how you can formulate it as an MPF problem. Then after we were done with that, then we shifted our attention to convolutional codes example. And here I started out by saying that we had many descriptions of convolutional codes along the way in this course, but the one that is relevant here is the one that is in terms of the state diagram. So, so this is the example state diagram that I provided for you just to remind you, and then we introduced some notation, and I am restricting myself here. Convolutional codes have a rate k by n, where k is the number of inputs and n is the number of outputs. Here we are restricting attention to the case when there is just one single input and then there are n outputs. And after introducing notation, I actually introduced this diagram. So, we will actually continue from there, but let me get to our current lecture. So, the current lecture is entitled Junction Trees. So, junction trees, so our goal is to actually provide an algorithm to solve the MPF problem, and it turns out that you may or may not always be able to solve the problem using this approach that we will outline, but in the cases when you can, the first step is to construct a graph which is a particular kind of a graph known as a junction tree. And we will come to that in due course, so I will skip that. So, recap, we cast the maximum likelihood Codeword decoding problem for the 742 code as an MPF problem. And so, let me quickly pull that up once. And then very quickly we followed that up by showing that for the same code you can have a second decoding algorithm, which is called the maximum likelihood Codeword decoding algorithm. For the same code we have two different decoding algorithms. One is maximum likelihood Codeword decoding, the other one is the maximum likelihood code symbol decoding, and the difference in the two cases was basically in one we were operating in the max product semi-ring, and in the other we were operating with the sum product semi-ring. So, that is one of the nice things about the approach that we will outline, that it gathers together in a unified way some different algorithms for different codes. So, the next thing that we did was did the same for maximum likelihood code symbol decoding of the same 742 code. Then I just got started in trying to formulate began maximum likelihood code word decoding of A rate of a rate 1 by n convolutional code. And we will continue on that. So, let me as a starting point pull up I think more or less the last slide from the last lecture. So, we will take this and copy it over. Okay. And so, here what I am actually doing is I am looking at a convolutional code with a small number of information symbols. So there are in fact 4 information symbols, which are U0, U1, U2 and U3, and then the convolutional encoder is initially in state S0 and subsequently goes through states S1, S2, S3 and S4. The corresponding received symbols are Y0, Y1, Y2 and Y3, and given Y0, Y1, Y2 and Y3, we are asked to recover U0, U1, U2 and U3. And I pointed out last time that Y0, Y1, Y2, Y3 are in general n tuples, okay, because your convolutional code being rate 1 by n, for every input symbol there are n output symbols. So, each of these is a vector actually. And I want to write down an expression for joint probability distribution based upon inspection. So, the way you should interpret this diagram is saying that if this is what is known as the directed acyclic graph associated to a probability joint probability function. So, if you think about the joint probability function of all of these variables, then this graph is actually telling you how it will factor. It will factor according to the product of PU0, PU1, PU2, PU3, PS0 and then PS1 given U0 and S0, because there are arrows leading into it, P of Y0 given U0 S0, P of S2 given U1 S1 and so on. Okay. So, this graph suggests how you would factor the probability mass function. The above graph so known as a directed acyclic graph and abbreviated as DAG, tells us how to factor the joint probability distribution function. So, it factors according to, so P of u I is equal to 0 to 3, comma S I is equal to 0 to 4, and Y I is equal to 0 to 3. The joint distribution function of all of these factors according to P of S0, the product I is equal to 0 to 3, P of U I P of U I times P of S I plus 1 given S I U I times P of Y I given S I U I. So, this is how it factors, and you can see that what the figure above showed us is that it is a graph that reflects this factorization, because there was an arrow leading from S I and U I to S I plus 1, indicating that there was a dependence of S I plus 1 on the values of S I and U I. Okay, you could see that here. For example, S2 is dependent upon U1 and S1. So, these probabilities affect the probability of this. Okay. Now, our interest is in maximum likelihood code word decoding of the convolutional code. So, what we will do is we will define f I of u I. We will define f I of u I to be the max over not u I of P of y given u. I think I already explained in the last lecture that there is a one-to-one correspondence between code words and message vectors, and which is why this can also be regarded as maximum likelihood code word decoding. So, in trying to understand how this accomplishes it, the argument is the same as we did last time. I will repeat it quickly. So, you compute this quantity for each I. So, there are 3 symbols. So, you will compute this for I ranging between 0 and 3, and you will actually compute it for each of them, and then you will compare f I of u I equal to 0 and f I of u I for u I equal to 1. Whichever is larger, you will choose the corresponding symbol. And the way to understand that this achieves maximum likelihood code word decoding is to pretend that there is one message vector u for which this quantity here is the largest possible. And then what you are doing is you are uncovering the symbols of that one by one, because when you do a comparison for u I equal to 0, let us say that the most likely code word had all its symbols to be 1. Okay. So, when you put u I equal to 0 and u I equal to 1, that code word will show up in the list corresponding to u I equal to 1, but it will not show up in the list u I equal to 0. So, since you are taking a max here, you will actually be comparing a larger quantity for the case u I equal to 1. So, in this way you will actually one by one be stripping off the message symbols of the most likelihood code word, and we saw a detailed example last time. Okay. So, once you understand that our goal is to actually compute this for u I equal to 0, u I equal to 1 for each value of I in this range. Okay. So, that is our goal. Then the rest is okay. Now, we need to formulate this as a MPF problem. So, we will do that. So, the first step is to actually say, well, since all message symbols are equally likely, so I will write this is equal to By the way, I think I explained last time that this tilde ui means that you are taking the max over all symbols u0 to u3 other than ui. Okay. So, it is the not, and we have seen that before. So, this is the max over tilde ui. I can write p of y comma u, and actually it is proportionate to this. So, it is proportionate to this, and the reasoning being that all message symbols, all message vectors are equally likely. Okay, so that justifies this step. And now what we are going to do is we are going to take the max equal to the max over tilde ui of p of y comma u comma s. And the reason for this, I will try to explain, is just that when you are, because what you are doing is, so maybe I should draw a small figure here. So, you can divide the set of all message vectors into those in which, let us say, ui equal to 0 and ui equal to 1, and here you will get for example, you will be computing p of y u for some vector u which is such that ui equal to 0, and here you will be computing p of y comma u prime for some u prime such that ui equal to 1. You will be computing, these are example quantities here. And now what this S does, so S of course stands for the state. Now given a message sequence u, S is completely determined. So what that means is that when you are computing the max over here, you are also taking the max, you are taking the max not only over the ui, but you are taking the max also over the max over all vectors S. And you might say, well, how can you justify that? How can you actually arbitrarily increase the variable set over which you are taking the max? Well, because basically you are taking the max of a set of real numbers, and in here what you have done is that to add to this original set, all that you have done is you added some zeros, because for any given message sequence and any given state sequence, there's exactly for any given message sequence there is exactly one state sequence which is consistent with it. So for a large majority of pairs u and s, this quantity will be 0. It will only be 1 for those which are compatible. So what you are going to do is here you are going to when you actually put in s, you are going to whatever I see when you were trying to decide between 0 and 1, you were looking at all these values and taking the largest value here, the largest value here, and listing them under 0 and 1 and choosing 0 or 1 according to which was larger. Well, now what is going to happen is that when you actually expand to include this new state variable s, you are going to have the same values in here with a lot of zeros thrown in. But that does not really change the fact that because when you are computing the max of all these and all these quantities are non-negative, you will still recover the same value, you will still recover the same value here. And for this reason this is actually justified. Okay. All right. Now I am going to actually expand this joint distribution function given our the directed acyclic graph here, right. This is also called a Bayesian network sometimes. So this is also called So, I should write perhaps that it is also AKA Bayesian network, because it tells us how the probability distribution factors. So, using the Bayesian network and the corresponding factorization, I can write this as the max tilde ui over all s of exactly the expression we had earlier, p of s naught I is equal to 0 to 3 p of ui p of s I plus 1 given s I ui p of y I given s I and ui. And this is where we stop, because now we have formulated this as an MPF problem, because you see that you have all these quantities here which can be regarded as local kernels, and you have a global kernel which is the product of local kernels, and you are marginalizing with respect to a certain set of variables. Okay. So, the only thing that remains for us is to identify the local domains and local kernels. Okay. So, the local domains are, in this case, the ui I going from 0 to 3 with associated local kernels p of ui. Then you have the perhaps to decrease the chance of confusion, let me write this not as a set, because each ui is individually a local domain. So, perhaps let me modify this slightly. So, this is ui associated with local kernel p of ui, and this is for I ranging between 0 and 3, and then you have S0 associated to P of S0, and you have Si plus 1 Si ui associated to P of Si plus 1 given Si ui, and then finally finally just Si ui associated to P of yi given Si ui. So, then these are your local domains, these are your kernels, and you can see that you have multiplied these and are marginalizing this. Okay. All right. So, the conclusion is we have thus formulated the maximum likelihood Codeword decoding of a convolutional code as an MPF problem. All right. So, now we will introduce a new subtopic, namely we will introduce the notion of a junction tree. So, we have outlined a problem, a class of problem called the MPF problem. We have shown how the decoding of some example code can be formulated as an MPF problem, and now we want to actually try to go ahead and solve the problem. And what we will actually be doing is we will be using the distributive law to give us an algorithm which is of reduced complexity. Okay. And the first step in applying the distributive law or the generalized distributive law, the GDL, the first step in applying the GDL is to attempt to organize the local domains into a so called junction tree. So, let us make a note of that. The first step in attempting to solve using the GDL, the MPF problem is to organize the local domains into a form of graph known as a junction tree. So, what is a junction tree? So, definition, a tree is a graph in which a tree is a graph is a connected graph in which there are no cycles. Okay. And couple of the generic example of a tree might be a graph that looks like this. So, a tree might look like this, and you can see that in a graph like this. So, these are nodes and these are the edges, and you can see that it is connected in the sense that you can go by traversing a sequence of edges from any node in this graph to any other node. And there are no cycles in the sense that you cannot travel without retracing your steps around the graph and land up at the same node at which you started. For example, if you start here, there is no way to actually come back to this node without retracing your steps at some point. Okay. So, yeah, so that is the picture you should have in your mind for tree, and just some observations about trees. We will call them nodes. Note, in any tree in any tree we have that the number of nodes or vertices minus the number of edges is equal to 1. Okay. For example, if you look here in this example, the number of nodes, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So, you have 13 nodes, and you define an edge as a link between two nodes. So, you have one between these 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, the number of edges is equal to 12. So, you can see that the number of nodes exactly exceeds the number of nodes number of edges by 1, and it is not hard to prove, but we will not do that. Then the other observation about trees is that between any two nodes there is a unique path. For example, if I wanted to go, let us say, from, let us call this node A here to node B, then there is exactly one path which will take me, and that path is to follow like this, okay, and it would lead me to this node, which would lead me to this node. So, there is exactly one path that I have to follow. In any tree, there is a unique path between any two distinct nodes. That is not hard to see, because supposing you had more than one path, then you would actually have a cycle, because you could go from node A to node B along one path and return by the other, and that would create a cycle. Okay. So, having defined a tree, what is a junction tree? So, we are going to define a junction tree in a certain setting. Okay. So, definition. So, in the setting of the MPF problem. Okay. So, let us quickly review what we mean by that. Okay, the setting of the MPF problem, this was from a couple of lectures ago, was where you had a universal set of variables and you had subsets which we call local domains, and you had local kernels, global kernels, and so on. Okay. So, there are these local domains though, and the idea is that we are going to call upon them in the setting of the MPF problem. A junction tree is a graph whose nodes are in one-to-one correspondence with the local domains x of S I going from 1 to m. So, there are capital M nodes, each one corresponding to a certain local domain. And where edges are drawn between nodes in such a way that 1, the graph is a tree, and 2, I will put on a picture. That is, that in the graph, so you see that these are some vertices that are associated with the local domains, and you are actually going from XSI to XSL and via the sequence of edges. And what the second requirement says is that if there is a variable that is in the intersection of Si and Sl, then that variable must be present along every one of the nodes that lie on the unique path between Si and Sl. Okay, so we will put that in words. So, the second property is if x let me phrase that a little better. For every node x Sj on the unique path lying between nodes XSI and XSL, it must be that x Sj is a subset of Si intersect Sl. And we will look at an example in just a second, but just quickly getting back to this graph, what we are saying is that on this graph, so here is Si and here is Sl, and so nodes Sj and Sk happen to lie on this unique path, and what we are saying is that take a look at the intersection Si intersect Sl, whatever variables are present must be present in the variables corresponding to each of the intermediate nodes. So, these variables must belong to Sj and Sk. Okay. So, the meaning is not so clear from the definition, but we look at an example. Consider we will look at the 742 code which we had examined earlier. Let me see if I can pull up something from our earlier discussion on that. Okay, here we go. So, this is the page that I want, and I am interested in the decoding of our code. Let me put, let me see, let me carry this slide. So, I am going to pick this slide. I am going to select this page and copy it. Okay, that is one. And then I am also going to copy a second page from our last lecture, which was where we had listed the local domains. So, this is the page. So, let us select the page, copy the page here. Okay. So, good. So, in our example, we are looking at the 742 code again, and here were the associated local domains. So, the local domains were the xi's, individual xi's, x1, x2, x4, and the question is, can you organize these into a junction tree? Well, then the question that comes up is, well, how do you actually organize these into a junction tree? So, we will look at that in a subsequent lecture, but I just want to show you what a junction tree looks like. So, I am going to draw, so I have to organize the local domains, and I choose to organize them like this. So, you can see that what I have done is I have organized all the local domains. By the way, whether I write, when I write 1 to 4 and put that down as a local domain, this is completely equivalent to writing down x1, x2, x4. Okay. So, these two are equivalent because they are just representations of the same local, different representations of the same local domain. Okay. So, now, so it is true that I have actually formed a graph out of them, and it is obvious looking at this graph that what I actually have is a tree. So, the question is this a junction tree? So, in order to show it is a junction tree, I have to pick for every pair of nodes, if I pick, let us say I pick, for example, if I pick this one here, this node here and this. So, here the SI is 3, 4, 6, the Sj is 1, 2, 4. The intersection between the two is 4. So, what I need to make sure is that on the unique path between these two nodes, which happens to be this, 4 is also included, which it is. Okay. Similarly, if I look at 1, 2, 4 and 4, 5, 7, on this unique path you must have every variable which appears in their intersection, but their intersection is 4. Okay. So, 4 also appears here. So, if you check this now, for the other conditions it is very easily checked, because 2, if you look between this node and this node, for example, their intersection is empty. So, that really places no constraint, right. So, this then is a junction tree, is an example of a junction tree. However, there is an alternative definition of the junction tree which is important both for the theory as well as for verifying that something is a junction tree. So, note an alternative definition of a junction tree is a tree which, when projected, and I will put this in quotes since this needs some explanation, projected onto each individual variable also yields a tree. So, example. So, let us go back over here, take this graph and paste it. Okay. Now, what I mean by projection is you take this graph and supposing you wanted to project it onto the variable 1, then you would retain all the nodes in which 1 appears and any edges between two nodes which are connected by an edge. Okay. So, here you would simply so let's do one thing, let's copy this page over a few times because we will use it a couple of times. All right. So, the projection, so let me put down that what we are going to do here is the projection onto variable x1. So, that is what we are interested. So, we ignore all the nodes which do not have 1 in them. So, none of these do. Okay. And so, there are only 2 nodes left, and we also remove the variables other than 1, and so we are left with this kind of a graph, and this graph is a tree. Okay. We require that in every such projection the end result be a tree. So, let us look at a second example. Here Here let us say I am interested in the projection not onto x1, but rather onto x4. I am interested in the projection onto x4. So, what I do is I do the same thing, I ignore all nodes in which x4 does not appear, okay. And then once in the remaining nodes I actually delete the variables other than sorry, I should have kept the x4, and I delete all variables other than x4 or 4 that appear. So, I am left with this. And now you can see that this is a tree, right. So, this is an alternative definition of the junction tree. The equivalence is not hard to prove, because after all in this graph what we required was that, for example, we required that if 4 is present here and 4 is present in this node, it is present in this node, then it must be present in all intermediate nodes that lie on the unique path leading from here to here, right. But that is equivalent excuse me, that is equivalent to saying that when you project this entire graph onto 4, that since 4 is presented in this node, the projection will have a node corresponding to this node, it will have a node corresponding to this node, and these nodes must be connected, and this is why the definition that the projection be connected is equivalent to the definition that 4 be present on the node of every in the variable set of every node that lies on this path. Okay, so the two definitions are in fact equivalent. So, now having done that, then the next question that arises, okay, so you define a junction tree, but how do I go about constructing a junction tree? So, this raises the question, how does one construct a junction tree? And the answer is that there are algorithms in graph theory which tell you how to construct a maximal weight spanning tree, and what we are going to do is we are going to adapt one of those algorithms, but first we have to actually make a connection between the two, between spanning trees, maximal weight spanning trees and junction trees. Okay. Answer by extracting, or rather by constructing a maximal weight spanning tree. It is not now in the literature, typically you will see references to algorithms for constructing minimal weight spanning trees, but it is not hard to see that you can actually adapt a construction for a minimal weight spanning tree into a construction for a maximal weight spanning tree. So, what is the connection? So, the connection is this. Theorem, if G is a graph whose nodes correspond to the local domains of an MPF problem and which is also a tree, which is also a tree then it must be that the edge weight of G must be less than or equal to the node weight of G minus n, where n is the number of variables, which is also the size of the universal set S. Okay. So, we just have had enough time to state the theorem. We will actually prove it in the next class, but just to very quickly summarize, what we have done today is we have formulated the problem of maximum likelihood decoding of a convolutional code as an MPF problem, and then I said that the next step in our discussion on the GDL is to show you how the GDL attempts to solve the problem, the MPF problem, and the first step is to construct what is called a junction tree. Okay. So, we will continue in the next class. Thank you.